Hi everyone, it's a great pleasure to be here with you for parity violation from home. And I'm here to tell you about parity violation in early universe and matter creation. That's an idea that I'm personally very interested in since it's about deep ideas in theoretical physics and QFT in curved space-time and its possible connection to the creation of our universe. I hope by the end of this talk, I can share some of this excitement with you, and I'm looking forward to all of your questions and feedbacks. Okay, let's get started. We know that our universe, the majority of the matter content of it today is made of dark energy and dark matter, and these are fancy names that we put on our ignorance about the real matter content. However, at least we know that 5% of that is made of atoms. And it means like the nanomolar of particle physics that are well understood. So it's tempting to say, oh, we figured out 5% of the universe. Unfortunately, it's not exactly correct since observation shows that our universe is highly matter dominated, meaning all the galaxies, stars, and clusters that we see are made of matter, and no sign of structures made of antimatter. In fact, you can quantify this mysterious asymmetry in terms of eta b, which is the imbalance between the number density of baryons minus the number density of antibaryons, rescaled by the number density of photons. And you get 6 times 10 minus 10, and this number is almost constant since the point of Big Bang nucleosynthesis until today. On the other hand, if you just put the standard model of particle physics and use general relativity, since both setups treating matter and antimatter almost the same, you expect to get equal amounts of them, and in the end, they get into thermal equilibrium and get annihilated. But so then you expect to have nothing. So how come we exist? To explain this unexpected asymmetry, we need physics beyond the standard model that provides sufficient CP-violation to generate a net baryon asymmetry. And there are several scenarios of leptogenesis and baryogenesis to explain this mystery. So a very common and popular approach is, of course, to assume that there are CP-violating phases in the neutrino sector that can actually provide the seeds of this matter asymmetry. The question that we are going to ask in this talk is a bit different. So here we wonder if it's actually the parity violation in the early universe that provides the seeds. More precisely, we're going to ask if, so can parity violating physics in the early universe through quantum anomalies provide the primordial seeds of the matter-antimatter asymmetry that we observe today? I divided this talk into 3 main parts. In the first part, we will have a brief recap of quantum fluctuations in cosmology, and then in part 2 and 3, we turn on sources of parity violation in the early universe and the corresponding quantum anomalies due to parity violation and its consequences for the matter production in the universe. Good. Now let's turn on quantum fluctuations. We know that quantum vacuum is not empty, but there's constant fluctuations around zero. So you have this vast ocean made of virtual particles, but on the average, still you have nothing. If you have a background field, and if this background is strong enough, it can actually upgrade these virtual particles and turn them into actual particles. And there are several elegant examples of this interesting phenomenon. And the most relevant one to our current discussion is the expansion of the universe itself. So here, comparing to the flat space that you start from vacuum, and then you have a virtual pair of particles that soon they will find each other and get annihilated. In an expanding universe, once you have this virtual particles, by the time they want to find each other and get annihilated, the space underlying them can expand so fastly that they cannot. So, for instance, in the very early universe, during inflation and reheating can actually happen. The first person who discovered this effect was Schrödinger. And then later on, Parker systematically studied this effect and this so-called gravitational particle production by using QFT techniques in curved spacetime. So the expansion of the universe breaks time translation symmetry, and as a result, the in vacuum and the out vacuum, which are defined in the asymptotically past and future in your cosmic evolution, are now different. And as a result, it leads to particle creation from the vacuum. Interestingly, however, Parker realized that if you put a conformal field in the cosmological background, a conformal field like, for example, massless fermions, since the cosmological geometry is conformally flat, then this conformal field cannot really feel the expansion of the universe because all the effect of the gravitational background you can just you can just remove by conformal scaling. So how to create fermions in an expanding universe? Of course, you need to break the conformal symmetry by introducing interactions. And the most well-studied and common interactions are to couple them with the inflaton field, a standard model, a dark sector, and so on. Or you can just consider these fermions to be super massive, so you can produce them gravitationally and in a sufficient amount. However, in this talk, our interest is in a different limit. We are interested in effectively massless fermions, at least during their generation. We want them to be nearly massless or exactly massless in a parity-violating cosmological background, when the conformal symmetry is broken by quantum anomalies that arises from the parity violation in the setup. So in a way, now the conformal symmetry is broken by the parity violation. Now let us break parity. Parity-violating backgrounds induce global quantum anomalies in chiral fermion sectors. And two famous ones are gravitational ABG anomaly and chiral anomaly. So the gravitational ABG anomaly is the anomaly of the fermion chiral current in the presence of a non-zero RR tilde. And the chiral anomaly is the anomaly of the chiral current of the fermion in the presence of a non-zero FF tilde. So in the presence of a parity-violating source, you can have chiral gravitational waves and that induce a non-zero RR tilde. And in case the source of parity violation is also coupled to the gauge field, it can produce chiral gauge fields as well and induce a non-zero FF tilde. Now, if in your setup you have a non-zero NL minus N right, meaning that the number of left-handed fermionic species is different than the number of right-handed fermionic species, then in this setup, you can actually produce fermions. In the standard model, for instance, NL minus N right is 3 because we have 3 left-handed neutrinos and no right-handed neutrinos. So these anomalies reflect the fact that classical chiral symmetry are broken at the quantum level when coupled to a parity-violating background. Good. Now let us start with gravitational ABG anomaly. So the first ingredient is of course a non-zero RR tilde that requires chiral or circularly polarized gravitational waves. It can happen during inflation or later during radiation era. During inflation, for example, there are two well-known examples. The first one is Chern-Simons gravity. When you modify the Einstein gravity with this interaction between RR tilde and a dynamical axion, or you can couple your dynamical axion to a gauge field. It can be abelian or non-abelian, since in this part the focus is on the gravitational ABG induced fermion production. The U1 case is not efficient, and that's why I will only focus on the non-abelian case. So this is within the context of axion inflation. Just a brief summary, your dynamical axion induce a non-zero FF tilde, so chiral gauge fields, and this chiral gauge field will provide a source for gravitational waves, which is also chiral, and therefore you will have chiral gravitational waves that induce a non-zero RR tilde, and as a result, the gravitational ABG anomaly during inflation that can lead to fermion production. And in fact, interestingly, this is a very generic feature of axion inflation coupled to gauge field to provide a generic setting for leptogenesis and matter production, to explain the matter asymmetry during inflation, because all the Sakharov conditions are satisfied. Good. Now, let us move on to the case of radiation era. In this case, let us be skeptical about the source of parity violation, and let's consider a phenomenological model for gravitational wave with a broken power law spectrum. So this power spectrum is the net. However, since this process is sensitive to the chirality of gravitational waves, we need the spectrum for each of the polarization states. So I parameterize that in terms of a chi, which I call the chiral spectrum parameter. But this process is sensitive to the evolution of gravitational waves as well. So even a chiral evolution, a chiral process for the generation of gravitational waves contribute to this particle production. And as a result, I need to introduce another parameter, which I call it B. And this B parameterizes the difference between the evolution of the left-handed and right-handed modes of gravitational waves. And that's why I called it gravitational generation parameter. Now, using the anomaly, you can calculate the number density in this setup. Interestingly, is also a broken power law proportional to this capital N, which is a combination of the peak of the gravitational wave spectrum and also this term inside the red box that is related to both of the chirality parameters. What is in particular interesting here is that let's just assume that chi is 0. So it means that the gravitational wave today is totally unpolarized. Let's say the chirality has been washed out for some reason. But the evolution and the creation of gravitational waves, there was some chirality there. Interestingly, the fermions remember that. So fermions remember parity violation in the early space-time. Now you can actually see the energy density at the time of the generation, and you see that has the same structure as gravitational waves, but the amplitude is smaller. Here we assume that these fermions are effectively massless during generation up to some point, and then after the temperature of the universe gets below some scale m, they become massive and non-relativistic. Then we can find the fermion to gravitational wave energy density ratio that we have in this plot. It naturally divided into three phases. Phase one is a transient part when bursts of gravitational waves of fermions are generated. Then we get to the radiative phase when both gravitational waves and fermions are massless, but the production is finished and they're just redshifting by the expansion of the universe. And eventually the fermion gets its mass, and that's the point that the ratio increases like the scale factor. And then by this gravitational ABG anomaly, we can produce both the standard model leptons or a chiral fermion as a dark matter candidate. A successful gravitational ABG leptogenesis requires a reheat temperature as high as 10 to 14 GeV and omega peak to be around 10 minus 6. So it's really close to the limit to be either confirmed or disproved by future observations. And then in case that these fermions are like dark matter, in this case, the mass of the fermion is unknown, and you can have a parameter space that we have here. In the horizontal axis, we have the mass of the dark matter, and in the vertical axis, we have the T reheating. The two bars in yellow are the conventional gravitational particle production predictions, and these two bars in red and green are the predictions of this scenario. When the solid line shows 100% of dark matter, and the dashed line shows 1%. And you see that, interestingly, it can produce dark matter in part of the parameter space, which is not accessible to the conventional mechanisms. However, it also requires a high reheat temperature as high as 10 to 10 GeV to produce all the dark matter today. Now, of course, there is another anomaly naturally happening in axion inflation. So remember, the axion inflation is a generic setting for lepto and baryogenesis because all the Sakharov conditions are satisfied, and naturally you have chiral gravitational waves. So in this case, that can also lead to fermion production. This case field can be either a U1 or a non-abelian one. In case of the non-abelian gauge fields in axion inflation, and in the context of left-right symmetric extension of the standard model, this setup provides a common origin for baryogenesis called dark matter production and inflation. And it prefers a left-right symmetry breaking scale above 10 to 10 GeV. And to summarize, a parity-violating cosmic background can induce quantum anomalies, which breaks the conformal symmetry of massless fermions and leads to their production. Remarkably, this anomaly-driven mechanism do not rely on CP-violating phases in the neutrino sector, and it suggests that the mysterious matter-antimatter asymmetry shaping the modern universe may ultimately trace its origin to the primordial violation of parity. And that invites future theoretical development and future observational tests. Thank you very much.